So my recommendation to figure out when you schedule is go and try to schedule, and it'll give you an error. Because I was confused about it as well. Oh, you mean like a wave like that? Probably not. If I were to guess, they have different circuits for different kind of waves.
Okay, guys, we have attendance 1101. Let's see, is the code.
Apparently, I have another one. Well, I can't find it. How do you like those? Yeah, they're so good. Like, surprisingly good. I have tried listening to music with my hands.
Okay, don't forget to do attendance 1101. It's the code. So we have midterm, second midterm, end of the week. I'm gonna put the time from Friday to Sunday night to everything be okay, to be aligned with rules, regulation in university. And yeah, it should be covered assembly code, RISC-V, and whatever we're gonna cover this week. So what we had last class and what we're gonna cover today. So we started, so the goal of this class we know is to see how a processor, a general purpose processor works in general. We had some abstraction layers. We finished instruction set, part of instruction set architecture. For RISC-V, we actually learned how to write some code in assembly language. And 2 weeks ago, we started talking about microarchitecture, lower abstraction layer than ISA. In microarchitecture, we're supposed to learn how data path and controller works. We started with ILU. So we learned how we do addition, how we do multiplication, and a division. So I submitted one video for division. I'm gonna cover that part very shortly today as well for your assignment. That is due date tomorrow night, I think. Don't forget to submit it as soon as possible. Some students asked me for changing the time. I think you had enough time, for doing that. I'm not going to change the due date for that. So yes, we talked about ILU last class, especially multiplication that can be done even parallel. That was very interesting. If you make a actually those partial products. To add them together, you can make a structure as a parallel structure to add them very fast. We had this same situation in division. So for division, this is the structure. Like a normal structure is not even optimized. As you can see, the registers are 128 bits. ILU also is 128 bits. It's like multiplication, but instead of adding, we have subtraction. To understand how this division works, I hope you took a look at that video that I submitted. Anybody had a chance to take a look at that video? Not yet? For your assignment, you have to look at that. Division is part of the midterm too. So take a look at that part. I'm going to explain that very fast now. So this is what data path for division works. So if you want to know how division works, you need to know probably in high school how longhand division works. In longhand division, I'm going to put an example here. Like how decimal works, same as decimal we can do with binary. Like for example, you have a number like 1000. That's a divisor. And you want to, and also you have a dividend. That dividend is, for example, 101010. So you want to find actually the result of dividing this by this. So to do that, you're acting like this. In this hardware, first you need to align divisor with a dividend. Dividend is gonna be in the same place as actually reminder. So reminder is also dividend. Okay, and when we go through a step by step, this dividend gonna change, and at the end, whatever gonna stay in this part is gonna be reminder. So this is how this algorithm works. So what we are doing, first you need to align them. Align them means makes them 128 bits if the numbers are 64, sorry. But here in this example, we consider each register just 4 bits. So what we are doing in divisor, you fill the lower part all with 0 and put the number in the highest part. And for reminder, you don't change anything. You just put it, whatever you have in as a dividend, you put it in reminder. So this is dividend. You put it here. It's, in this case, is 8 bits. So the rest gonna fill with 0. If here we have 7, so the last one is 0. So we fill it with 0. So how this algorithm works, we are doing subtraction. So first, so we have 1 0 here. I change the color. So we subtract this with this. If the result was negative, we put 0 as a output. If the result is positive, we put 1, and always shift this to the left. So first, this is negative. The result is negative. We don't need to even compute the result. If the result is, why is negative? Because the second value is bigger than this. As you can see, we have 1 here, and here is 0. So the result is negative. So we put the Q, the output, we consider that Q. Q is 0, and we shift this one. When we shift this one, we remove 1 0 from here. We add another 0 there. And now we do subtract again. In this case, the result is positive because it's all 0. And when we subtract, how we do subtract, we can do second complement. And here we have 0, 1, 0, 1 as a result, and rest are 0. So we shift another one. We shift another one. We put 1, 0 here. So again, this number is smaller. So the result is negative. We put 1, 0 as a, we forgot to put the 1 here. When that was positive, we put 0. We put 1. And then another 0, shift again is negative. Another 0, again negative. And then the result going to be like that. And when we put, actually it's like this, 0, 0, 0, 0, 1, 0, 1. This is not negative anymore. This is positive, so we put 1. And as you can see here, we started from 1, 0, 0, 0, and we ended up to 0, all 0, so it means it's done. So 10 is bigger than 0, then 10 is the remainder. So this method of division is the method that we were using in high school. We call that longhand division. However, we changed that here with filling this part with zeros and shifting to make that simpler to implement using hardware. In your assignment, you need to kind of change this design. Instead of having 128 bits, you just use 64 bits. However, this reminder needs to stay the same, but this ILU can be just 64-bit ILU. And the divisor doesn't need to get shifted. You just can use similar to the design that we had for optimized multiplication. That's for your assignment. You just need to have one example of that. I already gave you the hardware. Just need to understand it and do one example. So this was regarding to last sessions, but still we are in ILU design. We want to talk about floating point numbers today. Floating point numbers are one of the complex part of designing processors. Sometimes, in addition to normal processor, we have another part or another extension for that processor just for doing floating point. In some computers, that's called coprocessor, just doing for floating point numbers. Because floating point numbers are complex, most of the time cannot be done in one clock, need multiple clock cycle. However, using pipeline can help. We can see that later. So before, the idea behind floating point numbers is to have very large or very small numbers. And in this example, I want you to, however, we had floating point in digital logic. I remember I covered that. But let's have this to see if you remember how we can implement a floating point number instead of just having bits in a structure that we had for integer numbers, how we can do floating point numbers. So I'm gonna define a pool. Let's see, start class and pool. Let's see how many of you knows this. Okay, I'm asking which, try to see if you can respond this. Which extension which expression is the best representation for floating point numbers? So because in floating point numbers, we have integer part and we have fraction part. So can we just add them together? Can we just have one integer or one binary number, including integer part or fraction? Is that help us for large numbers or small numbers, or others? Let's see how you think about that. Most of you guys try to do it all, okay? Yeah, most of you guys are right, and you specified B. That is correct. So it means that the idea is to have big numbers. How we can have big numbers if we just consider integer part and fraction? We can do that. But if we have fraction and actually using a base power something, so we can have very big numbers, because exponential numbers, like a power of something, it can be a very big number. So yeah, that's correct. So the B is the best answer for that. But let's see how that works and if there is any standard or something that we can use. Okay, so and this. Yeah, so the best answer is B. We did all correct. So for floating point number, we have some standard. The best standard that is almost 30 years we use this standard, and nobody changed that or add something new to that. It's called IEEE floating point format, or 754. IEEE 754. This format has two types for floating point number, because for floating point number we can have actually two types of precision: single precision and double precision. Single precision, the structure is like that. It's 32 bits. For double precision, you are using 64 bits. So for single precision, first bit is always signed. 8 bits for exponents and 23 bits for fraction. In overall is 32 bits. And that's for single precision. So for double precision, you are using 62 bits in overall. Again, most significant is always sign. How we can consider sign, we can see that. We have exponent, in this case 11 bits, and 52 bits in overall is fraction. So the fraction is 20 bits from the one word, and the rest of the word, that is 32 bits, as an extra fraction part. So we had the 52 bits fraction, 11 bits exponents. So this is double precision. So the math behind is coming from this formula. So the number, the output number that we want to model it using binary number, coming from these three parts: sign. If this S is 0, it means the number is positive. If the S is 1, because it's power of 1, we're going to be negative. So S, if S is 1, the negative number. If it's 0, it's positive. So for fraction, we are adding that with 1. So we put fraction here, but we always put 1. We added with 1. We can explain it why. And for exponent, we have bias. Bias is actually a number for, I think I wrote that bias somewhere. Yeah, here. Bias is 127 for single precision and 1023 for double precision. Why we need bias here? Because this exponent is unsigned. So to keep it unsigned, we consider, but in reality, we have negative exponents. So how we can manage that? We are adding that by a number to become actually unsigned, and we put unsigned here. We can have example to see how that works. So that's the structure for IEEE 754. IEEE is actually it stands for Institute of Electrical and Electronics Engineering, something like that. It's very famous. If you want to publish papers, publishing paper in IEEE is it's very good, and also there is lots of regions, IEEE regions around the world, but most of them in the United States. 1 to 6 region 1 to 6 are in United States, 7 in Canada, and the rest are in Europe and Asia. So yes, IEEE is, and it has a format even for writing. When you want to, when I ask you, for example, write your assignment or your project based on IEEE format, you can follow that for it. It has like a different style and fonts and a structure for IEEE. So it's good. You guys, if you want to publish something, follow these standards as well. So there is lots of other standards that coming from IEEE, like networking, Wi-Fi. They are all coming from IEEE standards. And this is one of them, floating point structure. That is for like 30 years that it didn't change. So it means it's good enough. It's good for designing floating point in computers. So structure is this formula as we explained. So there is some questions here why we add that by 1 and why we consider exponent minus bias. I explained that a little bit, but we need to see one example to understand that better. However, most of you guys probably know this in digital logic. Let's have this example. So I asked you change a negative number to this structure, IEEE 754. First, you need to change it to binary. How we can change that to binary? Normally, if you remember, you need to multiply that by 2 every time and take out the integer part, and again multiply fraction part by 2. Any integer part coming out going to be the digital numbers that coming out. Like in this case, for example, 0.75 multiplied by 2 is going to be 1.5. That 1 go out as one of the binary numbers after 0, okay? And then this multiplied by 2, like the 0.5 multiplied by 2 is going to be 1. And then the integer part, again, going out. And because this fraction is 0, we are done. So that's the binary numbers for 0.75. So it makes sense because this one is 1 over 2 plus 1 over 4. If we add them together, this is going to be 0.75. But it has a minus that we need to consider that as well. So 0.75 in 10 is equal to 0.11 in 2. Okay, any question about that? Probably you knew that from before in digital logic. But if you don't know, you can go take a look to understand that. Anyway, that's how we do that. But this is not the answer yeah, this is the binary, but this format is not IEEE format. So we need to change it to IEEE format. How we can do that? First step is to normalize it. Okay, I didn't explain what normalization means. Normalization in binary means put the number in this format. 1, x, 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 whatever bits that you have, to power e. This e called exponent. This part called significant or mantissa. So that's how we do normalizing. Normalization means shift that to right or left to make just one as a integer part. Why we do that? Why not? We can because we don't need to store this one. All of the numbers can start by 1. If it's not starting by 1, it's 0. So any number that we want to represent using IEEE format to start with 1. So we don't need to store this one. I mean, store that in a structure. So that's why we can have this actually normalized. This is normalized. Normalized number. So this is for base 2, but for base 10 also the same. For base 10, you just need to have 1 digit this side. You are not allowed to have 2 digits. So for example, number like 3, 4 multiply 10 is not normalized. Why is not normalized? Because we have 2 digits here. We can write this as a 3.45, 10 power 2. This is normalized. Okay, so this is the first step to do. So this is denormalized, and this is normalized. So that's the second step, normalize the number. So to normalize that, we multiply that by 2 power minus 1 to normalize that. So maybe right now you got the idea why in the IEEE format we add actually a fraction by 1. That's the reason, because we already took that one off and we don't need to store that. It's always 1. So we just need to consider that 1 always. And yeah, we're going to have more example to see. Okay, so that's the part that we need to consider as a step 2, normalization. The next step is to consider the format. Let's clean this up. The format was like that. So the number is this. So this part is actually exponent minus bias. And this part, we don't consider 1, just that part. I mean, this one is actually, because here is 1 plus that, so it's actually this. That's all together. Yeah, that's actually 1 plus fraction. So it means fraction is, first of all, the sign is negative number, so S is 1. Let's clean that part. And bias is 127 because it's single precision. We are assuming single precision. We also ask double precision, but first we start with single precision. So for single precision, the bias is 127. So because this -1 is exponent minus bias, and bias is 127. So the exponent going to be 126. And so the binary of that should be this 0, 1, 1, 1, 1, 0. And for fraction, so the fraction is this is fraction, actually 1 plus fraction. So the fraction is just 0.1. So this is like a 0.1. This is the fraction. And when we add them together, that's for sign, because it's negative. And this is for exponent, step like this part. And this is the fraction part. So if we put them together, this is 32 bits corresponding to that number in IEEE format. So this is how we change to binary numbers in IEEE format. For if we consider double precision, you can do that at home. For that case, you need to consider 11 bits for here and 52 bits for that part. The sign stays the same. Any question about that? So I think we had that last semester in digital logic too, but we didn't go deeper. We can look at that a little deeper today. So if we change it to hex, it's going to be like that. Okay, let's look at the range for single precision and double precision. So if we consider single precision, in single precision, we have 32 bits, 1 bit for sign, 8 bits for exponents, and fraction is 23 bits. We want to see what is the maximum and minimum number. So we need to consider two things. We have some reserved exponents. These reserved exponents are for some specific cases in actually floating point numbers. For example, for 0, we have a little problem. Why? Because we are adding fraction always by 1, how we can consider 0. So if this is the 0, and this is 1, and minus 1, and minus 2, and so forth, and 2, and so forth to plus infinity and minus infinity, all of these two parts can be covered with this structure that is actually normalized. But for this case, we can't put this normalized structure. I mean, the normalized structure that I mentioned is the structure that was actually S minus 1, S 1 plus fraction 2 exponent minus bias. This is structure called normalized structure. For this specific range between +1 and -1, because we are always adding that by 1, so these numbers are smaller than 1. How we can add that by 1? That's the interesting part. So we need to consider that as a denormalized. Denormalized structure is a little different than normalized. We're going to see that is like that. -1s. This part is the same. For fraction part, we don't consider 1 plus fraction. We just consider fraction. 0.f is, imagine f is fraction part. And instead of 2 power e minus bias, that bias was 1027 for double, 1027 for double. In this case, is 2 power minus, we don't have E here anymore, you know. So we just consider minus 1022. Okay, we're gonna see that because the exponent is always this. We don't consider that part because we are just doing fraction. We are between 0 and 1. We just need to have fraction part. So we're going to see this special case that's called denormalized. Anytime that so we want to use the numbers between -1 to 1, we need to use this structure. This structure is denormalized. We're going to see an example soon. Okay, so I just wanted to mention that. Let's go for the rest. So yes, these two numbers, these two exponents are specific exponents. Anytime exponent is 0, this is reserved. That for the denormalized numbers. And denormalized numbers are this structure. Or for 0. When you want to show 0, again, 0 is a specific case that you can't show that with normalized structure. Anyway, also for infinity, if you want to show infinity or NaN, that is not a number, going for not a number, because sometimes you are dividing something by 0, for example. That's not a number. And in that case, exponent is always 1, 1, 1. Why we need to have this NaN or infinity? Any idea why we need to have this case? The first case is, you can guess, yeah, we need 0. We need numbers between 0, between -1 and 1. I mean, between them, not equal with 1 and -1. What about the next part? Why we need a specific case for infinity? Can we just consider the biggest number infinity or smallest number minus like infinity? We can, because any bits you consider, still you can have something bigger than that. Because infinity is not something that you can actually measure it, or you can fit it in a limited number of bits. You always have something bigger. So that's why in maths, we consider that some specific case as a infinity and not a number, NaN. Okay, so this is a special case. So if we take these two special cases or reserve exponents out, what we have as a minimum and maximum. Let's clean this up. So let's consider a smallest number. Okay, for a smallest number, exponent part cannot be 0, start from 1. Okay, if the exponent part start from 1, so if it start from 1, so that's the smallest exponent. 1, 0, 0, 0. 8 of them, because 8 digits. And for the biggest one is 1, 1, 1, 1, 0. Because we took out those reserve exponents. So this is 1, and this is 256. So if we want to find the number corresponding to that, we need to find the fraction. So the actual exponent is 1 minus this. 1 minus 126 is 1 minus 126. And the smallest fraction is all 0. So the significant going to be 1. And if we put them together, that's a significant. That's the number, considering this actual exponent. So this is the smallest number that we can consider for single precision. Is small because minus 38 is very small number, but still for many applications is not enough. For some applications, we need smaller than that. That's why double precision also exists. For biggest number, the exponent is this one. The biggest exponent is because we took infinity out, so that's the smallest one. And so the actual one is, because this number is 254 minus this bias is going to be that. That's the actual exponent. We have actual exponents. And what is the fraction? The maximum fraction is 0.1. And 1.01 is approximately 2. So the value is this number. If we change it to decimal, is going to be something like that. 3.4 multiplied 10 power 38 is a very big number, but it's still for some applications not enough. For example, you are measuring like molecules of something. In some cases, it's bigger than that. So that's why we need to have double precision. For double precision, instead of having these 8 bits, we're going to have 11 bits here. So the numbers change. However, this bias is also changing. I can compute one of them, but it's not that difference than this. Is very similar. So for double precision, that was for single. For double, exponent is actually a smallest exponent is 0, 0, 1, same, but is 11 bits. Here was 8 bits. So 11 bits gonna be, the number is still 1. And this is the biggest exponent, can be 1, 1, 1, 10, 1, and 1, 0. This number is 2046. So the smallest number gonna be similar to the other one. 1 multiply 2, 1 minus 10, 22. And the biggest number gonna be something like 1.7, 10, 3. Oh, if you change it to 10, let I write it 2, like 1.1, lots of 1, 10, 10,000, 1023. This is 1022, 10. So this is for the minimum number and the maximum number for double precision. As you can see, when we change that to decimal, is going to be 300 something. It's good enough. It's enough for at least for applications that we need for physics, for simulations, and so many other applications can cover with these numbers. Okay, that was a range of these numbers. As you can see, we can have variety of numbers and in continuous applications. Because in modeling, because the idea of using these numbers is modeling. Sometimes the things that we want to model is a discrete model. For discrete number, integer numbers are enough. But for continuous models, we need continuous numbers. And for those, we need this kind of standards. and we want to see how we can model them, how we can actually show them in binary case. That this standards is very helpful in this case. So the people that designed this system, they were very smart people. They considered all the details. And sometimes studying them gonna give us idea of how we can model this stuff. It's give us lots of ideas that if we want to design a system, how we can consider all of these tricks and parts that we need to consider in our design. Okay, let's have another example for this specific case. Imagine the normalized number. Number between 1 to -1, we can't use this structure. For this type of numbers between -1 and 1, we need to use another structure that's called denormalized structure. In denormalized structure, as I explained, we have -1s. The structure is like that. X is equal to this. This is for double precision, but for single precision also we have something similar, just that number is going to change. 2 minus 10, 22. So for example, imagine I ask you, S is 0, exponent is 0, okay, 11 bits 0, and fraction is 52 bits, but all 0, the last one, the least significant is 1, 52. What number is this? Okay, that's example. So we have S0, like a big 64-bit digital number. The most significant bit is 0, exponent is 11, 0, and the fraction is 52 digits, binary digits, that the last one is 1. Okay, we have this case, and we want to see what is X corresponding to that. So in this case, first of all, S is 0, so the number is positive, because it's going to be 1. Anything power 0 is 1. And the fraction part, the fraction, we don't change that. We don't add that by 1 anymore, because the number is between 0 and 1. So we write that up like this, 0.001, and multiply 2 minus 22. Sorry. Wait a second. What is that coming? Oh, sorry. This is two. Yeah, that's correct. 2 power 10, 22. So what is this number? If you remember, I just explained each of these bits. This is corresponding to 1 over 2. This is corresponding 1 over 4. And the last one is 52. 1 over 2 power 52. When we bring it up, it's going to be 2 power minus 52. Multiply to this. That you need, because they are both negative, you just need to add them. 2 minus 10, 74. So that's the overall number. So this is the number corresponding to this example. That was just example of the normalized numbers. For those specific range, we need to have this structure. Okay, so this was something that I should explain. Yeah, I just wrote that again here. That's a specific case. Instead of having this structure for normalized numbers, we have this structure for denormalized numbers between -1 and 1. So I'm just going to cover this slide and the rest next class. Floating point addition. To add floating point numbers, we always need to make these exponents similar first. So as you can see, this is the normal numbers, decimal numbers, but they don't have a similar exponent. So first thing is to make the exponents equal. That's the first step. That's called aligning the exponents. So after aligning the exponents make the exponents equal, this power equal, then we can do addition. We are adding fraction part, and when we get the result, the next step is to again normalize it. We are normalize that again. This is the normalized part because we need to have just one digit here. This is a decimal, so this number can be between 1 to 9. It cannot be 0. This is important. It starts from 1 to 9 in decimal. Okay? And that's the normalization. And at the end, we need to round it up. Why we need rounding? Any idea? So when you make that, maybe your register is just 4 bits. You made a 5-bit output, so you need to round it up. So rounding means instead of having, for example, this fraction, we round that the 002 fraction. That's called rounding. But rounding sometimes makes problem. Why? Because when you round it up, sometimes it makes the number denormalized. So we can see that next class, how we can solve that. Anyway, we can do the same way with binary. I'm just going to cover fast, but we're going to cover next class. We're going to explain that more. The binary is the same. So we start aligning, adding significance, and then normalize it and rounding. Hardware is also the same. That's a hardware for that. As you can see, 2 digital numbers, same standard, IEEE, and the result is also standard. We are aligning them first. We find which one exponent is smaller, shift them up, and then make them equal, add them up, and here is rounding part, normalizing and rounding. As you can see, we have loop. Sometimes rounding denormalize the number, we need to normalize it again. Okay, so next class, we're going to cover that more. Okay, see you next class. Have a good day.